me thank our speaker, those individuals that make these lectures free for all of us. Last week, I thanked Research, Discovery, and Innovation, the VP for Research at the University of Arizona, and TEP. They've been the flagship folks that have been paying for most of the costs here. But in addition to that, there's a list of individuals and organizations that have been supporting this for many years. And today, I'd like to just point out two of them. One of them is the Marshall Foundation, and the other one is Holualoa. Holualoa Investments, the person that's the president of Holualoa is Michael Kasser. I don't know how many of you know Michael. Michael is incredible. We have a theater in here that I think in large part is due to Michael's funding, and not only funding, but pushing hard for that thing to be successful. He's given money so that we have amazing athletics at the University of Arizona, and he's supported the College of Science and other entities of the university with great gusto, as he would say. He believes in arts and sciences greatly. He is probably the most extraordinary individual I know. He knows like 7 languages, and I hate him for it. And he got a PhD in chemical engineering and a master's from Harvard and an MBA. So anyway, he's one of those individuals that make you feel small every time you talk to him. But not really, because he is always the same Michael Kasser in his Hawaiian shirt. He is really all Tucson. And the Marshall Foundation, many of you have been here for a long time and know that if you go from Park Avenue to, let's say, 4th Street, and even less, that place was not very nice 10 years ago. The Marshall Foundation has created an environment around the University of Arizona that has made it welcoming, that has supported the university's mission, and in addition to that, supports the university's mission by giving funds for fellowships and scholarships and endowments for faculty. And I want to thank both Holualoa and the Marshall Foundation for all that they do for our community. Thank you. So today we're in for a treat. You're going to hear Feryal Ozel. Let me just say what my job is about. I mostly hang around and tell people that things are all great, but one of the things that I do which makes my job really extraordinary is that when people come to the University of Arizona and they apply for the job, or we're trying to bring them to the U of A, I get to chat with them more or less right off the bat. And when I met Feryal, it's one of those things that you sit there in front of intelligence and grace and quality, and you go, holy smokes. If I had to compete with Feryal for a job anywhere, I'd be screwed. That's a scientific term, by the way. So Feryal is in astronomy. When I first chatted with Feryal, she was chatting about a job in physics, but she's comfortable in the field of physics and astronomy. Astrophysics is probably the best way of talking about that. She's an absolute expert in black holes and neutron stars. She is wanted by every committee international that is out there for her intelligence and for her advice and where astrophysics should go. The details of her degrees are really irrelevant, because you're going to hear her today and you're going to say, wow, this is something really extraordinary. But just so you know that I do know it, she did get her bachelor's degree from Columbia. She got the degree with Cum Laude. And she went to Niels Bohr, where she got a master's. And she got her PhD at Harvard. She came to us because we're as good as she is. And it is time for me to remind you that every time that NSF shows the rankings of the quality of programs, astronomy always ranks #1 in the country. So Feryal is one of the reasons why that's the case. So please welcome Feryal Ozel, who's going to tell us, oh, before I do that, because I think it's important, it is important to just say the following. Today's lecture is a second of what we would more or less call the scientific method. The first lecture, for those of you that were here, pointed out the importance of double-blind experiments, the statistics of doing work with randomized tests, and how in the end you can only approach certainty. I think the lecture was extraordinary, and it very clearly pointed out the importance of the generation of statistics. Now, just to make it clear to all of you, double-blind experiments and randomized experiments are not only the purview of biology. I was talking to my fellow dean at the College of Science, Elliot Shue, who's a particle physicist, who pointed out that in particle physics, blind experiments have been used for a long time to get rid of bias of physicists. So it comes in all flavors. But today we're going to talk about what in science we call laws, and even though we may not know why these laws exist, these are issues in science that we can use to try to understand the parts of the universe that we cannot see. And I will leave it at that, and I will let Professor Ozel describe what she's going to talk about. Thank you.
Thank you. Thank you very much for that gracious introduction. Indeed, degrees don't matter. What is fun is exploring the universe, and that's what I'm hoping to do with you tonight. So we're continuing on our journey on searching for certainty. Last week, indeed, we heard about experimenting. And this week, I want to tell you about how, as astronomers and astrophysicists, we can say things about the parts of the universe that we can't directly see. But before I tell you how and are we certain and what is the search for certainty, what does it involve, I want to begin with a few facts about our universe. First is the fact that our observations with many telescopes in many different wavelengths of many different types of objects have told us that the universe, by and large, is occupied by things we don't see. So, to be more precise, we now say that 68% of the universe is made up of dark energy. So when we count up all the sources of matter and energy in the universe, 68% of it turns out to be a form of energy that we don't have direct understanding of. This is the energy that makes our universe expand faster than it should, and we have many different observations that point to that. Of the type that is more matter-like, what we've found out is that 27%, so about a factor of 5 more than normal matter, is dark matter. Dark matter is the type of matter that we can feel through its gravitational interaction. It doesn't emit light at all. In fact, it doesn't have any interactions, magnetic, electrical, or any other type of interaction apart from its gravitational interaction that we can directly observe with our telescopes. Okay? Of everything we look at, 5%, or 4.8% to be more precise, is things that we have tested, meaning stuff that makes up our bodies, our planet, stars, the stuff between stars, gas clouds, and anything else in the universe that shines and whose light reaches our telescopes. Now, of this 4.5%, even among the things that we say are normal matter, there is a class of objects that we don't see directly, and this is the black holes. So what are black holes? Well, black holes are collapsed dead objects. They can be formed from collapsed stars, like things that are maybe 20 times more massive than our sun, Or they can be at the centers of galaxies. In fact, when we look around us, in our galaxy, there are dozens of black holes that are more like this small type, what we call stellar mass. And around us, when we look at each and every galaxy, at its center, there are black holes whose masses reach 10 billion times the mass of our sun. Okay? So, different types of unseen things, dark energy, dark matter, black holes. And I said, let me just begin with a few facts about the universe. Now let's stop and take stock for a second. How many of you, and please don't be shy about this, think that I'm downright crazy? Show of hands, please. Okay, at least one person is honest. Okay, how many of you think this is more like a Star Trek kind of thing? That I'm not crazy, but maybe it's science fiction as opposed to science, that this is not astronomy. Okay, there are some who are admitting to that. Well, at the very least, when I said all of this, none of you walked out. At least I couldn't see anybody walking out. None of you laughed. So you probably thought to yourselves, there must be a way of knowing things that we don't see directly, and she must know that. Probably that's what you thought. Indeed, there are some rules of the game, and we apply these rules pretty diligently in order to gain an understanding of the universe, whether or not light from these objects reach our telescopes directly. What I would call rule number 1 is the exploration phase. We do our best to build bigger, better, and different types of telescopes in order to look far, in order to look all over, and in order to gain all bits and pieces of information that we can. We don't just build optical telescopes, we also build radio telescopes, we also build X-ray telescopes, because there are things in the universe that are at different temperatures that shine differently. We also put telescopes in orbit around the Earth. For example, this image right here is a piece of what is called the Hubble ultra-deep field. Meaning, this is from the Hubble Space Telescope, and it is from a patch of sky that Hubble stared at for a very, very long period of time. And what we saw were thousands of galaxies. You might say, how far is this? Are we really looking as far as we should? Well, this was a patch of sky that, to our naked eye, would look like nothing. In fact, it was chosen to be one of the emptiest parts of the sky, so far away that it would look like a nothing dot in the distance, completely empty. So we are indeed doing our best in terms of looking far, looking deep, and exploring in every way that we can. But there is a second principle that we follow, which is not exploration, but it is more about our methodology. And I would say this is even more important than the exploration one. And I'm going to call it, do try it at home, understand how it works, and then apply it to the other parts of the universe. So if I can make a tabletop experiment in a laboratory and understand how objects move or how forces between them behave, I can for sure apply this to objects in the sky, or if I can now look at things in the solar system and understand how stars behave in my galaxy, for sure I can assume not just my neighboring galaxy, but a galaxy halfway across the universe is also going to behave the same way. Okay? So, unlike the usual warning that we hear, kids, don't try it at home, we actually do want to try it at home. Okay. So, one of these ideas is that motion in the universe is deterministic. I should be able to understand why a particular phenomenon happened. Okay? I'll give you an example. Everything that we've done, every experiment that we've done, and this is not even a new idea, in fact, it's one of the pillar stones of modern science, tells us that objects left to their own devices, travel in a straight line. Okay? If there is no force on them, no influence of another body on them in whichever way, that they will travel in a straight line. If I now take the same object, and it does this, I know for a fact that there is another object that curved its path. Otherwise, it would have traveled in a straight line. Do I know exactly what the nature of the interaction between this and this is? Not really, but I can tell you that there is one. And in fact, it's even more powerful than that. If this is some bright, shiny object versus something quite dim that I can't directly see, I can still tell that it's there. In fact, this is the whole idea behind Planet 9. Not Pluto. Pluto is, it's still kind of demoted. The real Planet 9 in our solar system. Believe it or not, when we look at the motions of the outer solar system objects, they are pointing to the presence of a body, a Planet 9 that is most likely twice the mass of the Earth and quite far away, farther than Pluto's orbit. That must be influencing those bodies. Have we seen it directly? No. Are we trying to? Yes. There are now 2 separate observational campaigns searching the outer solar system, mosaicing where we think it should be, and trying to get direct evidence for it. But this has happened before. Neptune was predicted before it was seen, and in fact, it's just the backbone of our understanding. So, since I talked about the solar system, let me tell you a little bit more about how motion in the solar system forms our understanding of how gravity works, and how I'm now going to use it to tell you more about dark matter and more about black holes. So, this is a view of the solar system we usually don't have. We are actually in the plane with all these orbiting planets, so we get more partial views of their orbits. But if we could see it from the top, you would see the inner 4 planets orbiting fairly rapidly and the speed diminishing as you go farther and farther out. Okay? Now, it's the observations of planetary motion that started what I would call physical sciences, or at the very least, observational astronomy started by understanding how objects and planets in the solar system move. Okay? So, what do you see? They are moving in nearly circular orbits. Would an object move around if it was left to its own devices? No. There has got to be a central body that is keeping it in place. So, this was, in fact, it's so monumental that it is considered to be the launching point of the scientific revolution. It was the Copernican view of the solar system that said the sun must be at the center. Okay? This is the first level of understanding in building a theory, what I would call an observational model. Simply finding a pattern that explains the data. It might not be quantitative, it might not be the most basic understanding, but certainly putting the sun at the center explains all of that. Now, let's look at it a little bit more closely. Now, the sun is at the center, but as data accumulated over time and more planetary orbits were determined, now scientists could not only look at where they are, but how their period, which is the amount of time a planet takes to complete an orbit around the sun, and their distance from the sun relate to one another. Okay? For circular orbits, this is just the radius, the distance from the sun, but in principle, orbits can be elliptical. So when we plot these data, what we show is cube of the semi-major axis. Semi-major axis is the distance from the sun, and square of the orbital period. And these are all the planets in the solar system. You see that they lie on a straight line. Okay? So now we're starting to build empirical evidence. And this is indeed what now Kepler used to build his laws of planetary motion. This is what I would call the second stage. I don't understand why the square of the period is related to the cube of the radius or the distance, but I know that they are, and not just that, but I know what mass should be holding these orbits in place. I know what is holding these planets in place, and that is the mass of the sun. So now, simply by plotting these data on a straight line, we can measure the mass of the sun. We never have to go with a scale and weigh it. I mean, we are, right? I mean, this is going with a scale and weighing it in a way. Kepler's laws are really fundamental in our understanding of the universe. I'm going to keep coming back to this again and again. Now, as a mini detour, I'm going to also take you through the next two stages, which is going from Kepler to a physical law. And that we owe to Newton. Newton was the one who formulated the specific force on bodies. And not just that, but the force between objects that are interacting through the gravitational force. He formulated it. He said that force is going to be as big as the one that is the two basically that are applying this force on each other, separated by their distance squared. The formula doesn't matter. But what is very interesting is that he's now thinking about the interaction between two bodies, how it affects each one of them, and now going from an empirical law to a physical law. Oh, I understand where it's coming from moment. Okay? So this is also a big revolution in astronomy. But are we certain that Newton is right? Have we now completed our full understanding of how we are exploring the universe and how gravity works? No, certainly not. In fact, physical laws are there to be revised. In our search for certainty, we get to an understanding where we can formulate a physical law. Then we make predictions of how it should work in situations that we understand, go make measurements, and then they either corroborate or they refute our theories. Okay? So what happened to Newton? Well, Newton's laws certainly work on certain scales, but they're not there to be the final word on this. In fact, they were broken when Einstein came around. Now, this is Einstein's law of gravity. It looks nothing like Newton's, right? So what Einstein said is that actually all this thing about forces and objects pulling and pushing on each other, this is all wrong. He came up with a completely different formulation, a geometrical theory, which we call general relativity. He said that masses of all sizes, even the smallest ones to black holes to entire galaxies, warp the space-time around them so that other objects that are simply around them follow what they think are straight lines on this warped space-time. So think of a sheet, 4 people holding every corner. You put a mass at the center. It bends that sheet. So now if I take a little ball and roll it on the sheet, what is it going to do? It's just going to go and follow the curvature of that sheet, right? So Einstein's formulation is completely different. Why did he do that? What was wrong with Newton's laws? 2 things. One is the practical reason. Newton's laws worked on predicting the orbits of all planets except the precession of Mercury. Mercury is the innermost planet. It is elliptical, and that ellipse rotates a little bit as time goes on. Newton's law predicted a precession, but not the right magnitude. And Einstein knew about this. But that really wasn't his motivation. He wasn't trying to fix it when he came up with this theory. If he was trying to fix that, he would have added a little term to Newton's equation and been like, I'm done. That's not what he did. He was actually working in the patent office in Switzerland, and it was the time when precise clocks were becoming available in Switzerland and trains were becoming more and more common. He reviewed a lot of patents for synchronization of clocks across different train stations. How do you know that the clock at this train station in Bern is showing the same time as in this train station in Zurich? He kept thinking about synchronization of clocks. He kept thinking about relativity of time. He formulated his theory of special relativity. And then he realized that's not compatible with Newton's law of gravity. So one of the most fruitful endeavors we can embark on as scientists is when we have two well-established theories and we find a place where they contradict one another. That's where we should go. So physical laws can be revised in light of new data, in light of contradicting theories, and we keep doing that in our search for certainty. Okay, let's go back to dark matter, black holes. I promised you some of that, and I said, we have tools, we can apply them, and one of those tools is going to be Kepler's laws. So, where do we know the existence of dark matter from? We know it from what we call the rotation curves of galaxies. What does that mean? There is a type of galaxy that's commonly seen in the universe called a spiral galaxy. So this is a face-on view. We can see it's not the closest one, but I like it because you can see the spiral arms here. And you can also imagine this galaxy rotating about its center right here, and the whole galaxy actually spins around this axis. Okay? All spiral galaxies do that, without an exception. So just like planets orbiting the sun or other stars, entire galaxies spin around their own axes. Okay? So this is now our neighbor Andromeda. It's a slightly more edge-on view, and I want to show you how we actually obtain these rotation curves. So this is due to the famous astronomer Vera Rubin of the last century. One of the things she noticed is that as we look further and further out in the galaxy, so smaller orbits near the center, larger orbits where the stellar disk ends, and all the way out here, where there seems to be a lot less matter, certainly a lot less light, a lot less stars. The speeds with which these objects rotate, these stars rotate, vary. So if we make a prediction using Kepler's laws about how fast this should turn, there isn't a lot of mass interior to it, so it should be pretty slow. But as you go further and further out, as you get more and more mass holding all these stars in place, then the speed should increase. But as you go farther out, just like the outer planets are now rotating more slowly than the inner planets, Kepler's laws tell us that the speed should decrease. Okay? So this red line here is the Keplerian prediction. Interestingly, if you are paying attention to what this y-axis is, this is the rotation speed in kilometers per second. So the sun is, well, this is not our galaxy, but it's about somewhere here in our own galaxy, the Milky Way, which also is a spiral galaxy. So right now, as we speak, we are being hurled around at 200 kilometers per second. Isn't that fun? Anyway, the numbers don't matter. What matters is that the data that they collected, Vera Rubin and her colleagues collected, said something completely different. Indeed, the speed increased at first, but then it stayed there, as if more and more and more mass was holding this galaxy in place and allowing it to rotate in this, with these huge speeds without breaking apart or matter flying off. So, very simple application of Kepler's laws. Either Option A, I have more mass there than I can see. There is some form of matter there that it's not stars, it's not gas, it's not dust, it doesn't shine, but it is there and I can see it. And I can feel it in the rotation curves. Keplerian prediction, dark matter. Or, what is option B? What happened to Newton? His law was wrong. So what if now the galaxy is all there is to it, and this is Kepler, and this is a new law of gravity? That's possible, right? We have to weigh both possibilities. And in fact, we do. Just like we have revised even Einstein's equations over time, we look for different modifications that could explain this phenomenon without resorting to things that we don't see. So the top equation is what I showed you first, what Einstein formulated first. It wasn't his first trial. He actually tried many different forms. And at some point, he put in an equation, which we now call, a term in the equation, which we now call the cosmological constant here. And then he went on to call it his biggest blunder. He said that is absolutely not there, but now with the accelerated expansion of the universe, we know that term is there. The cosmological constant or something like it exists. So why stop here? What if there are other terms in the equation that simply weren't discovered before, or that weren't motivated by data before? This is only one form among many that I could have written. So what do? Now we have a framework, we apply Kepler's laws, something's got to give. Either there is dark matter, or there is modification to our law of gravity. We turn elsewhere. We say, okay, if it is dark matter, we're going to have to see it in not just individual galaxies and their rotation curves, but in clusters of galaxies, huge bodies in the universe that contain hundreds of galaxies. And this is a gallery. These are all individual clusters, some of them named up here. So what do? We go count up the light that they have in terms of everything that emits. Then we go weigh them through their gravitational interactions, and we compare the two. Is there dark matter or is there not? There is now overwhelming evidence that there is far more, 5 to 1 in fact, more dark matter or more matter in the universe than the standard luminous matter that we are used to. We didn't stop there. We started devising experiments to tell the difference between the option A, dark matter, and option B, the revised law of gravity. This is a famous example called the bullet cluster. We didn't make this happen, but once we saw that it was there, and U of A scientists were involved in this observation, we certainly knew what to do with it. This is a very interesting case. These are now two clusters of galaxies that have collided with one another. In fact, they have collided and have gone past each other. Dark matter doesn't have any interaction other than gravitational, so it can glide through more easily. Normal matter has other interactions, electromagnetic, for example, so it's more viscous. There is more friction, so it moves through a little bit more slowly. If this is dark matter, then what we expect to see is that more mass should go through one another and less light should go through one another. Is that what happened? So this is a Chandra X-ray image showing you where the majority of the emitting gas is. Because they rammed into one another, this is a shocked gas, and there's a lot of light coming out of here. Let's compare it to the mass map of the bullet cluster. The mass is further away. So there is one center belonging to the smaller cluster here, and one center belonging to the bigger cluster here. So if I now overlay them, you see that most of the mass has gone farther apart, and the light is interior to it. Ha! Is this the smoking gun? Is that why we call it the bullet cluster? Not really. There is a way to explain this with modified gravity, but it looks a little bit different than explaining it with dark matter. So even though this was a very big evidence, I would say, in favor of dark matter, even this didn't settle the debate. So the search goes on. So the search for certainty goes on. And we devise different experiments. Of course, in the meantime, we also set up experiments where we can detect dark matter particles directly. We look for what it could be at CERN, at the LHC. We do tabletop experiments. We do dark matter interactions. If it has any sort of interaction, can we see it with other devices? So that's how we're going to keep on looking for more and more and more evidence for dark matter, and at some point either be completely convinced or find an alternative, which we're happy with. Okay, switching gears, I want to tell you about the other unseen in the universe, which are black holes. Let me introduce you to one that I love in particular. It's the one at the center of our own galaxy. It's called Sagittarius A star because it's toward the constellation Sagittarius. And it was initially discovered as a radio source in the sky, which is this object right here. It looks a little bright in this picture, but actually it's kind of wimpy. It's not a particularly bright source. Like we've seen many brighter sources across our galaxy, but this is the dead center of our galaxy. So this is the dynamical center, and this is that radio source. Now, like good scientists, we want to take a closer look at the center of our galaxy. So over time, we've built bigger telescopes, better technologies like adaptive optics, and we have gathered lots and lots and lots of data on stars that are in the vicinity of our galactic center. Okay? The star cluster is called S. I know it is super imaginative, and the stars are called 101, 102, et cetera, et cetera. But what I'm going to show you now is real data. Even though it has been turned into a time-lapse movie, these data were collected over 23 years. The time will be running here. And each time you see a dot here, let me run it for you, it is real data. So these are individual stars at the center of our galaxy, 26,000 light years away. And we, just like our forefathers, the early scientists, followed Mars's orbit and Jupiter's orbit, we are now following these stellar orbits that are very far away, very dim. We switch to infrared light so we can see a little bit farther. We use adaptive optics. And at the end, you probably saw that this diligent, repeated observation of the same field again and again and again to trace out the orbits have given us two very fruitful results, which is that the closest two stars have completed a full orbit over these 23 years. What are they orbiting? I don't know. I don't see anything, do you? But maybe, just maybe, by using their orbits, I can get some information about how big the thing they're orbiting is. What would I use? Any ideas? Kepler's laws? Yeah, Kepler's laws. I know if something is orbiting something else, how big the mass should be that holds it in place. Okay. It is 4 million times the mass of the sun. What is holding these orbits in place? And yet these orbits are tiny. And they are very far away. But if the object that is 4 million times the mass of the sun was anything like normal stars that we see, that object would shine brighter than our sun. And I don't mean at the distance of the sun. I mean from the center of our galaxy, it would look brighter. It would overwhelm the amount of light that we get from our own sun. Certainly that's not happening. Instead, it's a relatively wimpy radio source. Okay? So, are we convinced? Yay, black holes. Certainly a lot of mass. It's not shining. It looks black, and Einstein's theory predicts the existence of these objects that collapse to nothing at the end of their lives. So are we done? Not really. Because we are searching for certainty, we actually go the next step. If these are black holes, not only should they contain a lot of mass in a small volume and look dark, but they should have a very peculiar property called an event horizon. It is the point of no return. That's basically the definition of a black hole. Not every massive object that is not emitting a lot of light is a black hole. It needs to be compact enough, its gravitational pull on its environment should be strong enough that at some distance from the black hole, even light cannot make it out. So there is a complete absorption of light into the interior. Therefore, the center of such a thing should look black. Okay? This is an animation that's showing you what would happen if I was shining light on a black hole. If the light rays were sufficiently far from the black hole, they would be bent a little bit, just like those motions in the bent space-time, the fabric, but they would go on their way. If they're coming too close, see what happens? They get bent so much that they end up in this circle of no return, and that leaves that signature that should be the signature of the black hole. Okay? Now, this is the very basics of the theory, but we want to put this into practice. We want to see if black holes have horizons. So what we discovered in the recent years, well, not that recent, I was actually doing my PhD when I first calculated this, but not only horizons should exist, but with the right wavelength of light, we should be able to see them. So what I calculated, this is in year 2000, is that if you look at long radio wavelengths, there is a lot of opaque material around the black hole. But if you start looking at shorter and shorter wavelengths, at around 1 millimeter, that gas turns transparent, and the hole in the middle should appear. So if we could take an actual picture of a black hole, not in visible wavelengths, but at 1 millimeter, our theories predict that A, we should be able to see down to the horizon, and 2, if it is a black hole with an event horizon, there should be a hole in that image. Okay? This is year 2000. Since then, we've built many, many different sophisticated computer simulations of black holes and their environments, trying to understand how black holes behave, how the gas around it behaves. So as gas gets trapped in this well, potential well going down to the black hole, for a while it heats up and it emits light, and that light is able to get away. We've built computer models of exactly how this light shines, how much of it can we see, and this right here is a compilation from many groups around the world, 6 different types of simulations, 6 different types of algorithms, physical models, and these are all very expensive simulations. Each one of them has been run on a supercomputer. Upper left one is ours right here at the U of A, my group's work. And you can see many different predictions. Why is this important? It's important because if we're going to go on this huge fishing expedition, taking a picture of a black hole and seeing if it has a hole in the center, we want to know what we're looking for, right? We want to be able to interpret our data. We didn't stop at this. At the U of A, using our computer cluster, Elgato, which was supported by the National Science Foundation, as well as the VPR's office, we looked at how this image could change over time. So not just the still, but if we did subsequent shots of images of the black hole at the center of our galaxy or in nearby galaxies like in M87, we basically made movies of how these images would change. Okay? So these are our predictions. It turns out that predicting something and actually measuring it turns out to be quite different, especially in this case, because the images that we were predicting turned out to be so small in the sky that it would be the equivalent of putting a donut on the moon and asking us to take a picture of it with cameras from here on Earth. Okay? Like literally a size of a donut at the distance of the moon. It also turns out that the telescope that has sufficient resolution to carry out this experiment is as big as the Earth. We went to funding agencies. We said, can we build a big telescope? They said, no. No, we didn't. We didn't even try. But we said, okay. Given we can't build a telescope literally as big as the Earth, how about figuratively as big as the Earth? And that is a concept called interferometry. What you do is you put a telescope here, you put a telescope there, you look at the sky at the same time, you record the data, you record it very faithfully, time tag it so you know exactly when your signal arrived, then you bring these two data pieces together, you combine it, and it is as if you looked at the source with a telescope as big as the separation between the two. In terms of collecting power, of course you don't have it. Your dish is your dish. But in terms of angular resolution, how big a telescope you have, how fine a scale you can resolve in the sky, it serves that purpose. Okay? So this is just a graphic that explains it. If I want to take a picture of this black hole, I put one radio telescope here. Remember, millimeter is the magic number, millimeter wavelength of light. I put one here. Light arrives at these telescopes at slightly different times. I record it, and then I correlate it after the fact, and hopefully I have an image that looks like a hole in the sky. Or looks like one of those images from the image library that I showed you just a couple minutes ago. Okay, so we've been working on this for about 15 years. We've been working on building a global telescope, what we call an Earth-sized array. For those of you who were in my talk a couple years ago, maybe you heard some of the ongoing efforts in building this array, and we were just getting ready in 2017 to make the first round of observations that involved all these telescopes across the globe. What did we do? Well, we're using our own telescope on Mount Graham, SMT, and this year, actually, we're working on putting a second dish on Kitt Peak. So this year's observations are going to have 2 Arizona telescopes. We also outfitted the telescope in the South Pole so we can literally span the size of the Earth. This is the Greenland telescope, our northernmost point and our southernmost point. 2 in the Atacama Desert in Chile, ALMA and APEX. ALMA itself is an array. It's a big, powerful telescope that we are lucky enough to use for this experiment. And a bunch of others. LMT in Mexico is a very important site. You can see how it's connected to all these other sites, so we can have all these pairs that are connecting the information and giving us more and more of that image that we're looking for. This took many years, and it took a lot of effort. So just one of those that I really like, my colleague Dan Maroney here at the University of Arizona. This is from one of his trips to the South Pole. He's actually there right now with 2 of his graduate students. This is a couple years ago. This is the South Pole telescope. And on a sunny, wonderfully warm day, what they did was put this receiver, you can barely make it out in purple, into the telescope so that they were able to record the right kind of data and do this experiment. You might also see his grad student right here, Junhan. It is so much fun to be a graduate student in our department. It took years of effort. So for those of you who were at the lecture last week, Joanna talked about these controlled trials and double-blind experiments. In astronomy, we don't have the luxury of controlling the phenomena, but we certainly have the luxury of designing our experiments. Here is my prediction. Here is the right place to look, the right type of data to get, and if it's option A, I will know, and if it's option B, I will know. So it's certainly an experimental science, not just an observational science, when you spend so much time building the right type of telescopes, equipment, experiments in order to answer questions. So in 2017, we did our first full array observations. Even though the array keeps growing, like I said, Kitt Peak is coming online this year. What we mean by full array is having both the east-west and the north-south large coverage that will give us enough resolution. And you can see from the happy faces in these pictures that weather was good on 7 different sites. And we need good weather because millimeter wavelength gets absorbed by moisture in the atmosphere. So we were lucky enough to get 5 nights of data. And at least I'm bringing you up to speed a little bit on what happened in the intervening 2 years. This is April of 2017. We collected 3.5 petabytes of data over those 5 nights. It's an extraordinary amount. And since then, what have we been doing? Well, first, we literally had to physically ship the data because it's so much data that you can't actually transfer it over the internet from location A to location B. Remember, we now have to collect all of these data centrally from the South Pole, from Greenland, from everywhere, and combine it and search for where they match up. It's so much data. FedEx took it to different places for us. So these are some of those hard drives being created and being shipped, and this is one of the correlation centers, one of the 2 correlation centers with disk after disk after disk of data. Okay? We did combine it. We calibrated it. We wanted to make sure that each telescope behaved as we expected, that it didn't get too little light for whatever technical problem. That calibration step is very important. And in the intervening 1.5 years, we've been working super hard on interpreting the data. So, as I said, correlate, calibrate, interpret, and we are very close. Unfortunately, I won't be able to show you what we see tonight, but we're close. I can tell you that later this spring, we will be able to release our first set of data with some results about black holes and what their environments look like. So I'm excited about that, but I'm just going to leave you with this. My daughter is here in the audience tonight, and she can tell you that the past 1.5 years is looking more and more like searching for serenity, as in, let's just be done with this. I'm working around the clock, as opposed to searching for certainty. But really, the question is, do black holes look anything like we predicted? Is it going to be one of these images? Is it going to be anything that is similar to it? Is Einstein right in this particular prediction? Or is there a place where Einstein's theory of gravity also breaks down because it's incompatible with our understanding of the microscopic world? Hopefully, we'll find something interesting that I can share with you. But I have to say, failing is not a bad option because it's job security. If we say, we understand everything about the universe, let's go home, that is not going to be fun. So we're just going to keep on searching for more and more evidence for our theories, and hopefully some will fail. Thank you.